Okay, welcome back. We're starting this new topic about these things that we denote with capital letters. And here is an example. Roll 2 fair, independent, 6-sided dice and call the result S. I should have said add them up. S stands for sum. Maybe that goes without saying. So roll 2 dice and then add them together to get S. And we're going to consider probabilities of the form the probability S equals X. Of course, this is the kind of thing we did before the break. We calculated probabilities of events. And for some individual X, this is exactly the kind of thing we were calculating. But now we're going to kind of look at this S object and see what we can say about it. This S thing is called, if you watch the video, you know, it is called a random variable. And random variables can be a little bit slippery, but are extremely useful in sort of organizing all sorts of probability calculations. So everything we did before the break, events, probabilities, independent, intersection, union, that is really in service of helping us understand random variables. That's the real thing, the way people actually work with randomness. So we're looking at these probabilities, and in Mathematize, I want you to find the maximum x value, which I call x star. So for what value of x is this as large as it can be, and what is the probability at that x star? I'll give you 1 minute to work it out. If you studied for the midterm, this is kind of midterm problem that could have been on there. In fact, there was one very similar to this with 2 4-sided dice, but this one was with 6-sided dice. Okay, let me give you 1 minute to work it out. Any questions or comments while you're working away? Okay. Good luck. We'll see you in 1 minute. Okay, I only have 47 answers. Who's still working? Who would need more time? Okay, nobody. Let's take it up then. Let's see what people said. Okay, so we're calling the sum of 2 independent dice rolls S. This is a convention that we use capital letters to denote random variables. So S, the spooky random variable. I guess it fits for October. It can be random. So what is the probability it's equal to different numbers? And let's see, where is it the maximum? This kind of thing, actually. I think we did this the first week of class. Let's see what it says, or what you all said. Okay. So 0, 4, 5, 6, 7, 12, 36. So you get a nice little tower here going up to 7 and then down. The correct answer is 7. So the plurality of people got it right. If you said 12, you have misunderstood the question. So 12 is the largest value that 2 dice could be. So if I asked you what is the maximum value of S, then a reasonable answer is 12. But I'm not asking you what is the maximum value of S. I'm asking you for which value of X is the probability S equals X as large as possible. So in other words, I'm asking for the maximum not of S, but the function that depends on X. That is the probability S equals X. And that one does have a maximum at 7. What is the maximum probability? So this is, in other words, this is where the function has its maximum. And this is the height of that function. We're at the maximum. What is the maximum value? What is the most likely value of S? And what did you all say for that? All right, 0, 5, 6, 12, 16, 36, 1 over 18, 6 over 36. The most popular answer was 22. Again, if you put in 12 for the first part, and you thought X star was 12, then you would have gotten 1 out of 36. But 6 out of 36 is the correct answer. This is the kind of thing we did in the first week of class. It's 7, and this is really the probability that dice equal 7, which was 6 out of 36. It's that diagonal of the big square you got on the first day, if you still have your little table. Okay, what is this problem doing? We're trying to set up this idea of looking at this function, the probability of a random variable being equal to x, which we'll see has a special name and is a nice object. We're going to say more about random variables shortly. Any other questions or comments about this thing or anything else? Okay, we're going to do a little quick recap of random variables over here, and then we're going to look at this function and give it a name. That's coming up. Okay, let's see what these things look like.
Okay, again, this thing's not working the way I want it to. See that duplicate slide slow? It's just
Probably you just need to close it and open it, because now it's confused that
it's confused.
that you.
Okay, we'll try that. We'll do that, and then we'll try to do it again. And do the slideshow. Okay, it is not confused. Okay, so there's a very small number of slides pre-posted here, and just so basically you know what you don't have to write out. So this is a very basic definition. Is it exciting? It is not exciting, but it's just a basic definition. Variable x is a random variable if the value it assumes corresponding to the outcome of an experiment is a chance or random event. So the idea is that we are going to, okay, I think that's working, we're going to have a function that's going to assign probabilities to events, well, it's a numerically valued variable, and there is chance involved on what that value of that variable is going to be.
I have a question.
Yep.
Could a random variable be something other than a number? Like, could it be red? Could x equal red? Is that allowed?
Well, it depends on, we can have our ways of quantifying the categorical variable red, and we can make those non-numerical values numerical. We can quantify them. We can convert them.
In my area of math, you just say whatever you want your random variable to be. So we would call this thing, we would call it an R-valued random variable. Say R-valued. And you can put whatever kind of thing you want. Sometimes in my line of work, we do R to the N valued. If you've taken linear algebra, that'll come up. Or you'll have, what else could you have? Oh yeah, okay, you'll have a Hilbert space. You'll have to take a H-valued random variable in a Hilbert space. So you can make your random variables. You can make them any kind of value you want. You just say, in this course, it's always going to be numbers, so you don't need to worry about any of this. Okay.
And this is what a mathematician can do. They can do anything they want.
Yes.
They are not confined to
Right, this is the beauty
bounds.
of math. Yes.
It is the beauty of math.
There's a question
you can do
here.
anything you want. Yep.
Yeah. Yeah, I would say it would be a red, blue, green valued random variable. Valued RV. So this would be a random variable that takes on either the value red, blue, or green, and each of the events x equals red, x equals blue, and x equals green are valid events in my probability space. You just, whatever you want, comma valued random variable. So R valued, red, blue, green valued, H valued, whatever thing you're working with.
Yeah. So statisticians are primarily concerned when we talk about random variables with quantitative random variables, but we do lots of non-quantitative, like categorical variables such as colors and that kind of thing. And then we take a look at how we can treat these categorical variables quantitatively. So we have some approaches to that. So statisticians do work with lots of non-numerical outcomes, which we can still attack quantitatively. I'll leave it at that point. Anyhow, So we're going to look at a couple types of random variables. We're going to start with discrete random variables as opposed to another type of random variable, which we'll see in a little bit. But let's just think of the idea of some kinds of simple experiments which generate discrete random variables. We've seen some of these. Flip a fair coin twice, let x equal the number of heads obtained. Okay, so we ask ourselves, what values can x take on? Well, you could have 0 heads, 1 head, or 2 heads, okay? So x could take on values of 0, 1, or 2. Roll 2 dice. We've seen this example before where x is the sum of the 2 faces. So before we just said, okay, here are the different outcomes we could get, and we were attached probabilities. But again, we could just change our notation to simply say x is equal to the sum of those 2 faces. So x could take on values 2, 3, 4, and so on up to 12. Draw 2 balls with replacement from an urn containing 3 red and 3 white balls. Let x equal number of red balls selected. Well, we could get 0, 1, or 2 red balls, so x could take on values 0, 1, or 2, just like the very top experiment there. Now, what would differ if we drew the 2 balls without replacement? The possible values of x would be the same, 0, 1, or 2. What would change would be the probabilities of x. Now, when I said with replacement, part of the idea here was to show you that x took on values 0, 1, or 2 in this last experiment here. It was 0, 1, or 2 in the first experiment as well. And in fact, those values of x take on the same probabilities. In a sense, from a probabilistic perspective, the first experiment and the third experiment are the same, okay? Now, what about this one? Flip a fair coin until the first head is obtained. Let x equal the number of flips required. Okay, so think about this one in your head. Flip a fair coin, and you're going to count how many flips you have to take to get your first head. So you flip the coin once, maybe you get a head, maybe you get a tail. If you got a head, x equals 1. And if you got a tail, you got to flip again. And on the second flip, given that you get to the second flip, you didn't get a head on your first time. On your second flip, you either get a head or you get a tail. And if you get a head on that second flip, then x equals 2. But if you didn't succeed on getting a head on that flip, you go to the third flip. And then on that third flip, you either get a head or you don't. What's the maximum number of flips we might have to get before we observe our first head? I want to know an exact number. It's a real big number. Well, how big could it be? What do you think? You want to go to infinity. Oh, my goodness, that's very big. The point is there any maximum possible value? No, there's nothing that says we couldn't just have things kind of just keep on going, just keep getting a tail, even if it's a fair coin. Okay, so this one's kind of an interesting one because x doesn't have an upper bound in the sense that we can say this is the very maximum possible number of values that we could flip the coin. Obviously, at some point we wear out or something like that. But in a theoretical sense, yes, we could just keep flipping and flipping and flipping for all eternity, it seems to be.
The other way I would say this one is I would say it's unboundedly large.
Unboundedly large, yes. That's a nice phrase. Draw one ball with replacement from an urn containing 3 red and 3 white balls. Let X equal the number of draws required to obtain the first red ball. If you think about this one, this here is really identical to this experiment here. Again, you've got a 0.5 probability of getting a red on any draw, but who's to say you just don't keep getting a white and getting a white and getting a white, and who knows how many times you have to go before you get that first red ball. Okay, so let's just, with those things in mind, let's just kind of think of a couple of notes on discrete random variables. So we do distinguish between discrete random variables where the random variable either takes on a finite number of values or what we call a countably infinite number of values. The term countably infinite is an interesting one, and basically being the idea that, again, think of flipping that coin, that you could keep on flipping and count, so you can't put an upper bound on it, but whenever you did get that first head, you could count to that point, okay? Maybe it's 346 trillion, 297 billion, 148 million, 312,000. I'm just trying to remember how many flips I went. And then it was 614 flips. Yes.
Well, the exciting thing about countable infinity is that it implies the existence of uncountable infinity. It's like if you were taking a nice boat tour and somebody points out and they're like, oh, this is our medium great white shark. Oh yeah, I guess they're medium. I've spoiled the answer. A medium white shark. And you're like, a medium white shark? Why is it a medium white shark? Well, there's something called an even bigger one, the great white shark. So the countable infinity, turns out there's an uncountable infinity. We're going to briefly talk about this later in the course when we do not discrete random variables. So for now, don't worry too much about it. It will come at you later.
Oh, so many infinities.
Yes.
Are there an infinite number of infinities?
No comment.
No comment. Okay.
Yes.
Okay. So I'll mention this. You're here at class. Really think about this idea of countably infinite. Why do I stress that right now? Well, I've taught many courses with probability, and I can tell you on tests, a very large proportion of students do not catch on to what countably infinite means, okay? So we want you to think carefully about what does it mean by countably infinite. Okay, so the probability distribution for a discrete random variable, we also call that the probability mass function. And why is it called a probability mass function? Well, we'll maybe get to that. But the idea of this function is that it will assign a probability to each possible value of the random variable. It'll assign something to each non-possible value of the random variable, but again, something we come along. And so let's just define a random variable x for the sum when 2 fair dice are obtained. Again, that's the example we started with in the mathematizer.
Well, actually, I called it S for sum.
Oh, you called it S.
Yeah, that's because I had lowercase x, and if I have capital X and lowercase x, then I get very mad when I have to say it out loud. So
yeah.
It's fine. I don't mind when I'm writing, but when I talk about it out loud, I like to have a different letter.
And I must admit that I sometimes struggle with, if I write on a blackboard, was that a capital X or a lowercase x, et cetera? And it's like kind of inconvenient. Most of the books in math stats will use a capital X and a little a lowercase x.
Yeah, this would be like if in calculus class they call every function f. It would be like in calculus class if they called every function x, and then you have x of x, and then you get very annoyed. That's what we're like in probability.
Yeah, that is what we're like.
Sorry, that's the world. You just have to know about capital letters. That's the secret. Okay.
Oh, Okay. So we could ask this question, what values can X take on with non-zero probability? And, well, the values that it can take on with non-zero probability are the values 2, 3, 4, 5, so on up to 12. We're going to come back to that one in a moment. So what we're going to do is just look at some ways to represent the probability distributions, mathematical functions, tables, and graphs. Well, we've already seen it in tables. Let's just go over the table again, and then we'll do a graph, and then we'll go back to the mathematical function. Okay, so we're on a piece of paper. So capital X equals the sum of the two paired dice. And so here's the probability distribution. As a table. And we are going to put in our X and our P of X.
Wait, what is P of X?
Oh, well, it's going to be a function,
function.
For the probability.
Could we write
X.
P of X?
We could write P
else?
of X. We could write, you want to write F of X?
P, I'm okay with P. We should define what it is. We should say P of X equals, and then we should fill in the blank. What is P of X equals?
Okay, well, we will do that. Okay.
Actually, this is, you know, you're always bothering me, Gary, about my bold P's. This is why I do a bold P. So we can have a function P of X. P has not been taken. P is available as a letter we can use.
We don't use those in statistics, not very often, you know.
Yeah, well, yeah, we're in dire needs of letters. We're always running out of letters.
We're always running out of letters. Which is, and then you run out of the Greek alphabet, and then you've got to go into another alphabet, and then you run out of that alphabet, and then mathematicians keep making up new symbols, which are weird and wonderful.
Yeah.
And which is why you can write mathematics, but typing it is a form of hell.
Actually, this is, I can't resist to tell you guys this. Do you know the symbol for countable infinity, Gary? Countable infinity. This is a size of infinity. And there's a letter that goes with it. It's the Hebrew letter Aleph. This is Aleph 0 is countable infinity. And it looks something like this, pretty bad. And then uncountable infinity. Well, okay, one type of uncountable infinity is Aleph 1. Oh my goodness, this is embarrassing. I didn't think I'd be drawing Hebrew on the board this morning. Okay, on the first uncountable infinity, let's say. So yeah, they ran out of letters, and they had to borrow the letters from Hebrew. Anybody know Hebrew? Is this okay, Aleph? I would say it's barely passing. Okay, let's continue.
Okay.
All right, let's go back to the regular letters.
Okay. I'm actually not going to define the P of X yet. Let's just put in our values here for our probabilities. So we said the X values that we could get with non-zero probability were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And our probabilities, well, okay, is the probability and I'll start just saying random variable RV, not to be confused with recreational vehicle.
Morning, I called the probability S equals X. So I called it S, but now it's capital X, so it's the probability X equals X, which sounds funny when you read it out loud because of the two X's, but it's the probability of the random variable capital X takes on the value lowercase x. And lowercase x is some number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
So what is the difference between the capital X and the little x? We try to keep this straight. In a sense, the capital X is the name of the random variable, and then the little x is the values that it can take on. So this is where we'll use this weird phrasing that the capital X takes on the values, can take on the values, in this case, 2, 3, 4, so on up to 12. So now when we say what are the probabilities, we recognize these. These are things we've done before. 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36. We hit our maximum at x equals 7, 6 out of 36, and then we start going downhill. 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. And if we were to sum these, we find that the summation of the P of x from x equals 2 to 12 is equal to 1.
Hey, what is that funny shape you drew?
My uppercase sigma?
Ah, it's another. We got Hebrew, we got Greek. It's an uppercase sigma.
They know that one.
Oh,
That's
they know.
That's a
Okay.
summation sign.
Who's seen uppercase sigma for summation before? All right, great.
Yeah,
Just me.
They're totally on top of this.
All right, never mind.
Okay.
I'll be quiet.
Okay, some of that. So we did it as a table, and there's a couple other things I could do, but let me just go to the graph again. The idea of a probability distribution is it assigns probabilities to all possible values of x. When I say a possible value, I'm saying a value for which the probability can be greater than 0, where the probability is greater than 0. We're going to clean up some stuff in a little bit, but let's just take a look at this graph. And this graph is called a probability histogram if you were to be picky on your graph. But all you can see is we're simply plotting the probability for each value of x, and it's got the values of x there. And it's this beautiful little stepped pyramid. Okay, so that was probability distribution as a graph. Okay. Okay, let's see. Okay. So we've done it as both a table and as a graph. And now let's express the probability distribution as an algebraic function. I could leave this for you for a challenge, but it's kind of a tough challenge. So do we want to do that as a challenge?
Why don't we leave it for them? I'll give you a hint. You need to know the sum of the numbers 1 plus 2 plus 3. You need to know the formula for the sum of the first n numbers.
Yeah, well, I think it's got, okay. No, I want to do it right now.
Okay.
Because I want to get the math down. Okay.
Let's do it.
Okay, as a function.
Here, I'll also do it as a function. We'll see whose function they like better.
Okay. Okay, I need my dot camera.
Dot camera.
So I'm just trying to think in simple ways here. Simple ways. I'm looking at this thing and looking at this, and I go, hey, think of that pyramid. Think of that pyramid. Well, on the bottom, I always had a 36 down below. And then at the top, I hit this maximum probability at 6 out of 36. And that was with x equals 7. So that was the highest probability. But then if I went to x equals 5, x equals 6, or x equals 8, I I dropped from 6 down to 5 out of 36. So I lost sort of like one step as I went one step either side of 7. And then I went down 2 steps when I went 2 away from 7. And I went 3 steps when I went 3 away from 7, and so on. So if I kind of think about that, I might come up with this. 6 minus 7 minus x, and put absolute values on that. Okay, does that work? When x equals 7, I subtract nothing. When x equals 8, 7 minus 8, I could have done x minus 7. It wouldn't have made any difference. I could have flipped this around. X minus 8 would be negative 1, but then I take its absolute value, so I'd be subtracting 1. But for 6, 7 minus 6 is 1. Again, I'd be subtracting 1. And if x is equal to, well, let's just take 10 for example. X minus 10 is minus 3. Take its absolute value is 3. 6 minus 3 gives us 3. And we've got the probability for x equals 10. And similarly, it works at the other end. So this will work. And it's not the only way to write it, but it works. But then we should mention that this holds for x equals 2, 3, and so on up to 12. And what happens if we said, well, what about x equals, say, 15? Couldn't I put x equals 15? And now weird crap will happen. Among other things, I'd end up with a negative number. That doesn't work for a probability. All we need to do is put in our expression that it's equal to 0 otherwise. So if I pick any value of x other than 2, 3, and so on up to 12, I just say the probability of that value occurring is 0. So I've stated a mathematical function.
Can I show them
now
my version?
Professor Nika's got his own.
I wrote it a different way. You guys tell me whose is better. It's mine. Mine's the smart-ass way of writing it. I listed them all out. This function is the same exact function that was written over here. Of course, mine's not as elegant, right? Mine takes a little bit longer to write, but they mathematically represent the same function. If you've taken calculus, you've been tortured to death with what are functions and when are two functions the same, and so on and so on. These are two identical functions. Yeah, you can always write it like this. Sometimes it's helpful to write it the smart way or the compact way, and sometimes this is good enough. So it just depends on what you need to use it for, whether or not you want to write it this way. I will tell you there's a really cool formula called the Sherman-Morrison formula. Maybe I'm mixing it up. For the sum of any number of dice. So there is, I'll let you look up the Wikipedia page. There is a cool for me. I don't know if it's cool for you. This is the kind of cool my wife would disagree with me. There's a cool formula for the sum of n dice that you can check out. And so there's a compact way to write it. No matter how many dice you have, it's going to be some crazy polynomial, not just an absolute value, but you end up with x squareds, x cubed, and so on. And see, I'll let you see Wikipedia. Okay, but now we must have a vote on whose formula you like better. Who likes the formula with the absolute value? And who likes the formula with the big list? Who likes the absolute value? All right, who likes the big list? Oh.
Okay.
All right.
Now,
I'll get you next time.
If we had the sum of two 100-sided dice, who would like the big list?
Oh, yeah. This is, okay, can I tell you a secret? In mathematicians, if we had the 100-sided dice, I would do this. I would do a dot, dot, dot. So I would replace all this with a dot, dot, dot. And I'd say like dot, 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 all the way up to 7 or 6 out of 36. So you can get away a lot if the pattern is clear. You could do a dot dot dot. And
You can do a dot dot dot.
You can also do a dot 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 when the pattern is not clear, and then you get in trouble. So you got to be careful. Okay, let's move on to something
Which,
else.
if you
Now I'm
wanted to
embarrassed.
program it, the dot dot
That's
dot.
true. The computers don't know about dot dot dot.
They don't know about dot dot dots
Yeah.
unless you
Humans
figure a way
only.
to program your dot dot dots. Okay, what's next? Well, I got to go back to the slides. Okay, back to the slides. Okay, so the next one we're going to introduce, and this is a very important idea, the idea of the cumulative probability function, or we often call it the cumulative distribution function. Okay, these are interchangeable. The key thing is that this is cumulative. Okay, so we're going to do some funky things here. And I'm going to go back to paper. Oh yeah, not yet. Don't want to show the next one yet. Okay. Okay, back to paper. Okay. And if I was to say anything on this, it's that I start off with cumulative probability functions, so we really think of this idea of cumulative probability, but most books will refer to it most commonly as the cumulative distribution function. But what we are accumulating is probability. So let's just go back and do that table again. We had x, and we're going to have capital F of x. And I'm going to use the capital F of x here rather than a capital P of x, because that one's probably even more confusing.
Yeah, people do like capital F for this one.
They do like capital F.
Mathematicians are weird.
Yeah. Well, true enough, but very charming as well. Very charming. Okay. Okay, so we do our values of x there. And I'm using a big probability here. This is the probability that x is less than or equal to little x. Okay, so the cumulative probability for x equals 2 is simply the probability x equals 2. That's 1 out of 36. But if we were to say what's the probability x is less than or equal to 3, the probability of x is less than or equal to 3, we got to go back to our table here, just kind of sort this out. Well, if x is less than or equal to 3, it could either be 2 or 3. I'm going to sum those two. And so we'll just note that f of 3 equals p of 2 plus p of 3. And that's 1 out of 36 plus 2 out of 36 equals 3 out of 36. Okay, 3 out of 36. And that's what I'm just going through and continuing to accumulate. For 4, it's going to be 1 plus 2 plus 3, 6 out of 36. And then for 5, we add another 4 out of 36. And then for 6, we add another 5 out of 36. And then for 7, we add another 6 out of 36. For 8, we added another 5 out of 36. Keep an eye on my addition. Things could go weird. 9, add 4 out of 36, 30 out of, that's a 30 out of 36. 10 is 33 out of 36. 11, add another 2, 35 out of 36. And then 12, we've got to be up to 36 out of 36 equals 1. Yes. And 12 is the highest probability, or the highest value, which can take on a non-zero probability. So since it's the highest number, its cumulative probability has to be 1. Okay, so we've got all that. Note that. Note f of 12 equals 1. Think about what that means. And, well, now we got a couple little mathematized questions. Let's ask a couple mathematized questions.
I know what F and P are. Does the questions just say, what is F and what is P? So hopefully you were paying attention. What is F and P? F, and we want to do F of 15 and P of 15, where F and P are the two functions we just introduced. All right, we'll give you 1 minute to try to puzzle out what these things could be. There's only a few seconds left. I guess we did a kind of a nasty thing. We asked them for something that you didn't do in the table.
I feel so guilty.
I don't. I think it's good. Okay. Okay, we're up to the last few people are getting in. Oh, it's still beeping. You have a few more seconds while I make it stop beeping. Okay. Capital F of 15, and again, we're talking about the sum of two dice. And you have to know that capital F is the cumulative one, and lowercase p is the probability mass function, the distribution function for a discrete random variable. What did people say?
Let's take up P of 15 first.
Ooh, this is exciting. What a good split. 16 people think it's 0, 22 people think it's 1, and 9 people identified that they don't know. Does not exist means they don't know. So that's a nice split. I think we don't know the answer for F of 15. What about P of 15? Maybe there was more of a consensus on P of 15 before we reveal the answer. Let's see. Okay, P of 15, that one seems pretty solid. People think it's 0. I think we told them that it was 0.
I
think they got it. That is right. So if you'll remember, the probability mass function, in my version, I had 0 otherwise. And I think you had that in your version too, didn't you?
I had it in my version too.
Amazing, okay. So if it's not on the list of things that have non-zero probability, it's 0. And I might another way you can do it is you just remember the definition. P of x is the probability that capital X equals lowercase x. So if you ask what is the probability the dice rolls come out to 15, well, the probability is 0. So that one is clear. But what about the capital F? Capital F, people are pretty split. Could go either way. And lots of people don't know. Let's remember the definition, and then we're going to do a revote. So the definition of F of lowercase x, it is the probability that capital X is less than or equal to lowercase x. So this is the random guy. And then this is the actual value you plugged in. So x is the value you plugged in. And we're taking the probability of that event, right? So the x less than or equal to lowercase x is some event. What is its probability? That's the definition. If you use the definition, you'll get the right answer. Let's revote this one. So I'm going to open it up one more time. Same exact question. And I want to see if you guys can figure out what is F of 15 on your own. Feel free to chat with your neighbor and see if you can figure out what is the right answer. Okay, I'm going to open it up again and give you 1 more minute to do it. And then we will go from there. Okay, I have opened it up again. Even if you don't want to change your answer, you have to put in your answer 1 more time. And I will give 1 more minute to think, use the definition, and talk to your neighbors and try and see if you can figure out what is the correct answer for f of 15. I have not said what the correct answer is. Okay, time's up here. So we didn't tell you the correct answer for f of 15, but we gave you some hints. And let's see if you were able to figure out the correct answer. Last time it was quite split. This time we have a big majority, 40 people are in 1. Almost nobody said they don't know. And 1 is the correct answer. The correct answer is 1. So again, f of 15 is just kind of a shortcut for what is the probability that the dice roll will come out to less than 15. So f of 15 is the probability that capital X is less than 15. This is the kind of question we did before.
Less than or equal to 15.
Less than or equal to, thank you very much. Very good.
Yeah.
Yes, less than or equal to 15. And in this case, it's a 100% chance that when you roll 2 dice and add them up, you'll get something less than or equal to 15. So f of 15 equals 1. Very nicely done. Should we give them the part 2 of the mathematize? Or do we have more things to say? I think
No, we can go right to the, I got it on the slide, but we can also just go to the mathematize.
The part 2 of the mathematize. Let's do the part 2 of the mathematize. I think everyone will get this one right away now that everyone is on board. F of 3.5 and P of 3.5. What is this? Okay, one minute. Okay, just a couple of seconds left here to get in your guess for f of 3.5. So last time we saw what happened when you're sort of past the range. Now we're seeing what happens if you're in between on a 0.5, right? Well, that's weird. Let's see what it is. Okay. F of 3.5, some people said 4.5. Lots of people, right around half the people said 3 out of 36. Some people said 3.5. Some people said 6. The correct answer is the plurality, 3 out of 36. And once again, you can unpackage it into the definition. So f of 3.5 is the probability that x is less than or equal to 3.5. What is the chance that the dice roll is less than 3.5? Well, the dice roll can only come out to 3, so this is in fact the equal to the probability that x is less than or equal to 3. There is no chance it is between 3 and 3.5, so I might as well just get rid of that in this case. And this one was 1 out of 36 plus 2 out of 36 equals 3 out of 36. That's what we did. What about the lowercase p value? What did people get the lowercase p value right? Everyone knew this one was 0. So this is the real reason that people like working with f sometimes, is it is an honest-to-goodness function that sort of makes sense for all the x values, whereas p is kind of a silly, like, spiky function that only makes sense on very specific values and is 0 a lot of time. And for that reason, p is sort of annoying to work with. But f is like an honest function that you would see in calculus. Let me draw a little graph of f. You might have seen it before. It looks kind of like this. So it has these little circles and dots. So this is what the function f of x looks like. This is x equals 2, I guess. X equals 3, x equals 4. It's one of those functions you would see in calculus class. All right, we'll leave it there, and we'll see everyone on Friday.